Let us start lecture 17. The course is on phase diagrams in single component and binary systems, and today we will be continuing our discussion on phase equilibria in single component, and we have taken H2O as a system, and we will also start looking at the phase diagram in single component, which is H2O system. In fact, in the last lecture itself, we have started looking at the phase equilibria between solid and liquid in case of water, and we could draw a boundary on the P versus T diagram. Okay. That is nothing but the demarcation line between solid phase and liquid phase, and on that particular line every point we have a condition of equilibrium between solid and liquid. So, today we will continue our discussion. We will try to extend that particular effect, that particular equilibrium when we talk about solid and vapor as well as liquid and vapor. In fact, solid and liquid both are considered to be a condensed phase, and it will convert into vapor phase. So, we will also look into that part as we go ahead in today's lecture as well as subsequently in the next few lectures. So, today we continue our discussion on phase equilibria and single component and phase diagram. So, if we see what we have done last class, we have seen a diagram which relates to this P T, and we have a boundary between solid and liquid, and the slope is nothing but dP dt, which is negative. Why? We have seen that del H m Tm Vm. Okay. So, in case of water, when we talk about solid to liquid as well as when we talk about solid to liquid, this one is a positive term, this one is always positive term, but this one in case of solid to liquid transformation, especially in water, this is negative. So, that is what this slope is negative, and we have a demarcation. We do not know where it ends. So, we are just giving, we are just we have just drawn this arbitrarily over P and T with a slope dP by dt equal with a negative slope, and we know one point which is 1 atmosphere and 0 degree Celsius. So, at this point solid and liquid both are in equilibrium, and we have also got some idea about this equilibrium condition where dG equal to 0 at constant pressure and temperature. So, this is 1 atmosphere and 0 degree Celsius, and we have reflected that through this diagram, GT diagram, where this is GS and this is GL, okay, free energy of liquid and free energy of solid, and these are all molar free energy. I am talking about the 1 mole change. Okay. So, these are all molar free energy. We have seen that too also. So, again if we consider 1 atmosphere, so this temperature would be 0 degree Celsius, and here we have some G, but if I try to draw delta G solid to liquid, so this corresponding point if I take it here, so I will get a situation, this is 0 value, through this I will get this particular plot. So, all the value and with reference to 0 value will be negative. So, this is spontaneous change from solid to liquid, whereas any value above this 0 line would be positive. So, it is basically non-spontaneous change. when we talk about solid to liquid transformation, or other way around, if we consider liquid to solid, that would have been spontaneous change. So, that is what we know. Now, today we will try to treat something with this particular plot, and we like to calculate at any other temperature, let us say here T prime, at that temperature what would be, or let us say this is a temperature T1 and this is T melting. Okay. So, this is T melting. At that temperature, what will be my free energy change? So, this change delta G, and since it is a molar I can put m. So, that change we need to find out. So, that treatment will do. Why that is important? Because as we go ahead and then start looking at binary isomorphous phase diagram, that time definitely we will be calculating and then find out how to draw isomorphous phase diagram with the measurable quantities, with the experimentally measurable quantities like melting point, enthalpy of melting, and then we will be using this particular value when we go for lower and lower temperature, starting from at a certain higher temperature to lower and lower temperature. So, that isomorphous phase diagram will evolve. An isomorphous phase diagram would look like this. So, where this is let us say A and B solution, B is concentration of B increases, and let us say melting point of A is lower than the melting point of B, and 100% here, this is 100%, and this is let us say TMB. So, isomorphous phase diagram looks like this, where this is liquid, this is solid plus liquid, this is solid. So, these phase diagram when we draw from this to when we go from high temperature to low temperature, we will be using this formula. So, that is what we will treat that. But before we treat that, let me just give you some examples of solid liquid transformation, practical examples, and its effect, it is a positive effect as well as negative effect. So, one example is this is, let me just draw, and then we will treat free energy change value at a temperature below melting point. So, this is example of solid liquid transformation. Okay. So, let me just keep the reference diagram, temperature, pressure. So, this is the diagram, and this is 1 atmosphere and this is 0 degree Celsius. Okay. Now, one example is why two ice block, if pressed each other, join once pressure is released. So, we started talking about this in the last class, so we will try to analyze that. And the second is why the rods in low temperature belt cracks. Okay. Or even I can give why pipeline carrying water in hilly areas, in mountain areas, fracture. Okay. So, that these two questions we will try to see. Now, if I try to see the first example, let us say I have two blocks, two ice blocks, I press each other. So, that means pressure goes up. Now, once the pressure goes up, let us say this is at 0 degree Celsius in order to understand it better. So, 0 degree Celsius and 1 atmosphere. So, once you press it, the equilibrium, so that means this pressure goes up. So, that means pressure goes up. So, let us say this is my new pressure P1. Okay. So, new pressure is P1. So, which is less than 1 atmosphere, more than 1 atmosphere. So, as we see that the equilibrium melting point, which is T prime, drops. So, equilibrium melting point drops. So, this is at T prime. When it drops, and melting is an endothermic process. So, when it is endothermic process, that means its melting point drops and it takes heat, and outside the surrounding temperature is 0 degree. So, when the melting point drops, that means it has to melt. So, this region local melting happens. Okay. And when local melting happens, the region also gets cooled because of endothermic process. Now, the second sequence is you bring back the pressure to 1 atmosphere. So, that means initially we have taken there, now we are dropping it here, which is 1 atmosphere. That means Tm equal to 0 degree Celsius, but when it is restored, this region temperature is still lower than, which is T double prime, let us say there will be little heat exchange. So, 0 degree Celsius. Since it is below 0 degree and there, so that means I am here, let us say I am in this zone. So, which is in the solid zone. So, that means that liquid will solidify. So, if solidifies, that means both the ice cube initially, because of the increase of pressure, both of them have melted locally, and that is a liquid. So, those liquids are mixed properly. Now, again that mixed liquid we are bringing it back to solid. So, that means it will be a fantastic union, solid union, and this two ice cube will join in. So, this is exactly happening because of this typical negative slope of dP dt for solid to liquid transformation. Fine. So, this is exactly the situation. Now, let us understand both this effect. Now, when we talk about, this is about ice cube joining. What is the advantage of it? You know, when we make ice cream from ice powder, okay. So, this is the exactly happening. So, what we do, ice powder, we put it in a mold and then we press it hard and then we pull it out, and in the meantime we push a stick into it, a small wooden stick, and then we pull it out from the mold, and you have a fantastic union of ice powders, ice flakes, and then after that you mix lot of syrup solutions. So, you make an ice cream out of that. So, this is basically one can make ice cream out of it. Now, if I try to, this is one, this is second part. Now, similar way, let us say daytime temperature, let us say its atmospheric pressure is 1 atmosphere, P equal to 1 atmosphere. So, melting point, equilibrium melting point for solid to liquid should be 0 degree Celsius. Let us say the daytime temperature temperature is greater than 0 degree Celsius, let us say 5 to 6 degree Celsius, fine. So, that will allow water in liquid form. Okay. Now, so this water, and let us say there is a small crack in the road. Okay. So, this water, liquid water can seep in, enter. Okay. Now, in the night time what happens? Temperature drops below 0 degree Celsius, let us say temperature is minus 5 to 6 degree Celsius, 5 to 6 degree Celsius. Okay. So, then this water in the cracks would become solid. Now, when liquid, so this was liquid goes to solid, and when liquid to solid transformation happens, same amount of let us say 1 mole of water, liquid water, or whatever amount is present there. So, there would be volume change, and this volume change is positive. Okay. So, now you have a situation as a small crack, there was a liquid. Now, in the night time temperature drops below 0 degree Celsius, and immediately the ice forms, and because of that volume expansion happens, and that is a narrow gap, and ice would try to find spaces to accommodate that expansion of volume, and in that way it will give a huge outward stress to that crack portion. So, you have a crack, and then ice forms here. So, it will try to put a tension on top of, on the opposing surface of the crack, and this will allow this crack to grow. And that way, if we continuously for example, there is a little bit of crack growth for a night, and then the second night again that crack has already expanded, you have another water accumulation, and again there would be a further expansion of volume due to ice formation. Like that way the road can be shattered because of that crack formation. This is again happening due to the typical volume expansion when liquid to solid transformation happens. And interestingly, so initial first day when there is a first night there is a small crack opening, now that solid inside that will again melt, because daytime temperature goes beyond 0 degree Celsius. So, that will try to seep into those crack growth part of that crack. So, that growth part of the crack is a narrow crack, still the water goes in, and then again there will be a kind of expansive tension given to the wall of the crack in the subsequent nights. Like that the crack will grow. This is one. Even similarly, when we talk about the pipeline, similar explanation. So, pipeline you have water flow, daytime or let us say it is a liquid, you have to keep the liquid form actually, because that is what you supply water in the hilly areas. So, now if there is a decrease in temperature and the temperature drops to a great extent, let us say minus 10 or minus 5-6 degrees Celsius, there could be possibility of that ice formation of that particular water flowing into the pipe, and that ice again is a volume expansion, it will try to fracture the pipeline. So, that means both the time you see that volume expansion creates lot of issues. Okay. And of course, this is avoided, this can be avoided. So, you see that sometimes we add salt, NaCl if you apply. So, NaCl what it does, NaCl plus ice, they try to form eutectic, okay, and temperature drops. Temperature can drop up to around minus 20 degrees Celsius. So, now you see, though the actual temperature is minus 5 to minus 6 degrees Celsius, but the water can remain liquid even up to minus 20 degree. So, that means water will not solidify. Okay. So, that is what salt mixture is added. So, we will talk about this eutectic effect when we talk about binary phase diagram. Okay. So, now you could see that there are couple of examples related to this typical phase transformation between ice and water, and that is reflected by a kind of demarcation line between ice and water, solid and liquid water on pressure temperature, and that plot looks that plot is a kind of straight line with a negative slope. Okay. You can actually call it a phase diagram between solid and liquid. Okay. So, we will extend this to solid vapor as well as liquid vapor. Now, let us come to the part what we wanted to discuss, that is finding. So, let us draw that reference plot G versus T, pressure equal to 1 atmosphere, we are fixing pressure. So, now this is G S, this is G L, this is T M. We are trying to find at T what will be my free energy change. Let us say this is for 1 mole substance. Okay. Now, in order to do that, I can write this as del S at T equal to T M, delta G equal to delta H M minus T delta S M. So, this goes to 0, which is 0 degree Celsius, and pressure equal to 1 atmosphere. So, then I can have a formula, have a kind of relation which is delta S m equal to delta H m divided by T m, and this should be T m. At T m it happens. Okay. So, this formula we get. Now, we will make it a generic equation, and then that can be applied to water system also. Now, now I am doing it at a different temperature, and this T is less than T m. That time I need to find out this as well. This should not be m. I need to find out this. These two quantities, if I can find out, then definitely I will be able to find out this. Now, in order to find out, we need to have some easily quantity which will allow us to calculate that delta G value at other temperature less than T m. So, now let me just find out delta H first, and we will see that these easily measurable quantities are nothing but delta H m and T m. Both can be found out using differential scanning calorimetry. So, this, in order to do that, let me just draw a picture where this is T, this is H. Let us say this is T m, this is T. Now, I start from here. Since it is below T m, it will be solid. Now, solid is actually, if I increase the temperature of the solid, solid will start increasing because of its Cp, and then it reaches to Tm, and then it starts melting. It will melt completely before the temperature start increasing. So, then again H value would increase. Let us say this point is 1, this is 2, this is 3, where from again all the melting happens and then it starts increasing again. So, this is H 1, 2, this is H, or I would say delta H, because it is a difference, delta H 1 to 2. So, then I should put 1 to 2, this is 2 to 3, and you see the slope is little higher than this solid slope. So, this is CPL and CPL is greater than CPS. So, that is why that I have put that slope little higher. Now, I have to find out free energy difference below melting. So, what I can do, I can extend this particular slope, I can extend this and then I can go to state 4 and then I drop down. So, I go this path. Okay. This is the path I will be following. So, this is delta H 3 to 4 and this is delta H 4 to 1. Okay. So, that is what the path will be, and this is basically what I am doing, that liquid I am enforcing that liquid below the melting point. That is possible, absolutely possible. Experimentally it is possible. There is a substance called glass. So, that glass formation relates to this liquid stability below melting point, but this is not a kind of discussion on glass formation, but I have just given you an example. Okay. Now, I know that H is a state function. So, if it is a state function, then del H should be 0. Circular, if I go to a kind of cyclic process coming back to the same state, then definitely this should be 0. So, I can write delta H 1 to 2. So, the final minus initial 2 1 plus delta H 4 3 2, because I am going from 1 to 2 now. So, here I am going 3 to 4. So, that is what 3 to I am going 2 to 3, 2 to 3. So, that is what the final number is written first and the second number where from the process started, plus delta H 4 3, since it is 3 to 4, plus delta H 1 4, it goes from 4 to 1. So, it comes back to 1. So, this should be 0. Okay. So, this should be 0. So, now I can write delta H 1 4 equal to, I can write minus delta H 2 1 plus delta H 3 2 plus delta H 4 3. Okay. Now, this one is coming out to be delta H 4 1, okay, just opposite. So, it is basically from 4 to 1 I am going. So, it should be 1 to 4. So, 1 to 4 is nothing but melting. Okay. I am considering in terms of melting. Okay. 1 to 4 if I go from solid, and this is liquid and this is solid. Okay. So, this is liquid and liquid line has been extended below the melting point, keeping the liquid stable, or I would say metastable. Okay. So, this becomes 4 1, 1 would be the initial and 4 would be the final. So, would be equal to, so this value is nothing but delta H m, which is the melting enthalpy. So, and that is should be positive, and this one is nothing but Cp S dt, which is T to Tm plus Cp liquid, this value would be, this is this one would be Cp dt and Tm to T. Then I can write delta Hm minus, I change the limit, Cpl minus Cps dt. Now, so this is one equation. So, this is basically for melting at a point below melting point. I can find the value through this. I need to find out Cp and Cp solid and Cp liquid separately. Now, I can also do the same treatment for entropy. This is temperature, this is S. A similar thing would be drawn. And here also this is liquid, this is solid, and this is melting, and S is also a state function. Hence, should be 0 cyclic process. So, I can write from here del S 41 should be equal to, and this is delta Sm 223. So, I can write delta Sm minus Tm Cpl minus Cps by T dt. Same process, you just follow exactly the same process, only in case of H you write S and you should get the same equation. Here also what I am doing, I am forcefully taking liquid below melting point from 3 to 4, and that is absolutely possible, as I have told you, practically this is possible. Okay. So, now we have to, now we know this value, how come? We have already developed that equation by Tm equal to delta Sm, okay, at T equal to Tm, fine. Now, entire thing comes to this. So, now if I can have kind of wild assumption, a crude assumption. Crude assumption could be, since that calculation of Cp is not easy. Okay. So, instead of that, I can make an assumption that Cpl minus Cps, which is del Cp solid to liquid, I am assuming that this value is 0. So, that means both are having same value over the temperature range what we have considered. So, if I take that consideration, then let us say this is one equation, this is second equation, both the equation I can write now delta H 41 which is melting solid to liquid should be equal to delta Hm, because this term would go to 0, this term would also go to 0, and delta 41 solid to liquid, or we can say 1 to 4, this is 1 to 4 would be equal to del Sm. Now, let me come back to the original formula, which is delta H minus T delta S at any other temperature below melting point. Now, I will just put those values. This is nothing but 41, this is nothing but 41. So, here I will put delta Hm minus T delta Sm. So, this becomes delta Hm minus T delta Hm by Tm. So, delta G would be equal to delta Hm Tm minus T divided by Tm. So, this Tm minus T is called undercooling. So, this quantity and these two quantities, all the quantities if you see, okay, are experimentally measurable, and they are measurable quite easily. So, you are getting free energy change from solid to liquid transformation at any other temperature below melting point through this equation. And these equation, there is a crude assumption which is Cp solid is equal to Cp liquid, okay, and entire process is happening at a constant pressure, fine. Now we see that free energy change at any temperature below melting point can be expressed through this, where this is the undercooling, okay. Now if I try to draw this free energy change with undercooling, delta T, which is Tm minus T, and delta G, and this is molar, remember. I can write M because we have started with 1 mole, molar free energy change due to solid to liquid transformation. In fact, this is 0 0, okay, and this particular point is equal to melting point, because I am considering the undercooling from melting point. Then I would see that this plot would be a straight line like this, where the slope is this particular delta Hm by Tm, these two are constant, okay, fine. So these two are constant, so that is what that decides the slope, and accordingly it is a straight line starting from 0. Now if someone takes a kind of a realistic approach without considering this crude assumption, where Cp equal to Cpl equal to Cps, or we start with a kind of situation where delta Cps to liquid is not 0, that time people have done calculation, those calculations are bit tricky calculations, and one can find out that with that actual change in the free energy change. So it would be like this. So up to a certain delta T, which is small undercooling, this two values, this is crude and this is experimentally measured Cp, these two merge each other. Not much of differences exist between delta G found out using crude assumption and delta G found out using experimental Cp data for both liquid and solid, or rather the difference of Cp data. So you will see that at a small undercooling they match perfectly fine, and they are very close to each other. The difference could be hardly 2 to 3%. So that would be absolutely fine, and we will see that this equation can quite well be used while calculating isomorphous phase diagram, and we will show it later also. So, and this undercooling is a very, very important aspect, and this undercooling is basically a thermodynamic quantity. Please remember that this is not related to cooling rate. Undercooling is basically the change in temperature starting from the transformation temperature. Here the transformation temperature is melting point. Okay. So, let me stop here. We will continue our discussion on phase diagrams in single component system. Thank you very much.